Hi everyone, this is MS Vishnu from ECE department. I have a case study on mathematics in roller coaster. Introduction. Mathematics is the science that deals with the logic of shapes, quantity, and arrangement. Math is also around us in everything we do. It is the building block for everything in our daily lives, including mobile device, computers, software, architectures, art, money, engineering, and even sports. Basic mathematical subjects such as calculus helps determine the height needed to allow the car to get up the next hill, the maximum speed, and the angles of ascents and descents. These calculus also help make sure that the roller coaster is safe. No doubt about it, math keeps you on track. Roller coaster rides are designed to look and feel more dangerous than they are, so that rides still get the thrills without significant risk. For example, teardrop shaped loop appearance more perilous than the simple circle. This is the image of that. It involves a less g-force on the riders upon entrance to the loop than a circle would, while still graduating the acceleration necessary to get through the top of the loop. Areas mathematics such as numerical analysis and different equations help solve the physics and engineering problems that arise as roller coaster designs, like riders sneak new records in speed, height, and steepness. Now we are going to see about the slope. Designers first sketch a roller coaster showing the placement of hills, twists and turns. Then they have to make more technical drawing in a computer aided designs program. This is where made become important. They have to calculate the slope of her roller coaster hills in order to construct an accurate model, one that the construction crew can assemble correctly. Also, the slope will also allow us to accurately determine the speed that will be generated at various points along the track. Loops. The most exciting roller coaster designs contain one or more loops. The loops must be built with the extreme precision. A loop that is too circular will require very high speeds. This would result in a g-force that is too high for people to comfortably withstand. A perfect roller coaster loop is a threadboard shaped called Coulthard loop. In a circular, the radius constant, but in a Coulthard loop, the radius changes and it's shorter at the upper part of the loop than it is across the center. This means the roller coaster can get through the loop at lower entry speeds. Advanced match functions are used to model Coulthard loops is computer program. Now speed. In order to complete a loop, a roller coaster car must travel at a correct speed. The speed is needed is dependent on the size of the loop. Every roller coaster becomes with a very high hill. The higher the hill is, greater the potential or shorter energy of the roller coaster car. When the car reaches the bottom of the hill, the potential energy has been completely converted into kinetic energy with the energy motion. That is when the roller coaster car reaches its greater speed. In designing a well functioning roller coaster, you must consider the following: speed, velocity, and acceleration, slope, maximum height, and minimum heights. Importance: the safety and assessment of the riders. Without calculus, roller coasters would not be able to complete it occurs safely, not efficiently. Engineers continuously use calculus when designing the loops and curves of roller coaster. Calculation: by using calculus, engineering can use the height of the slope of a point to calculate the speed. These calculations are used to satisfy regulars. Engineering is also used to speed a velocity equations to calculate the maximum and minimum height attainable by the roller coaster. Engineering principles in a roller coaster. Calculus applications. Engineering carries out calculations such as finding the velocity at the maximum height of the loop to see if the g-force is safe. This is the image of that. For this new loop, the designers will have to calculate the new velocity at the loop top and using a new height. The G felt will also need to be the rectangular using the two new ride. This lift has an exterior for the readers. Calculus applications continued. Speeds, the accelerations and velocity of the coaster are also very important. Use speed, take a derivative for the velocity, take a derivative agents of acceleration. Distance, maximum height of the coasters are measured using calculus, can be found where slope goes from positive to negative forming a curve, or where the derivative function across from the positive to negative. These are the examples and example functions. Derivative, critical points, maximum value at t is equal to 2.8, minimum value t is equal to 8.3 more. Example continued error. Speed, velocity, acceleration at maximum of on the 2.8, speed 22.2 meter per second, velocity 0.56 meter per second, accelerations minus 4.96 meter per second. Conclusions is a critical part of the designing of roller coaster. This is used to notify engineers of speeds, velocity, etc. At many different points along the track. This information is used to make sure that all passengers are safe when they ride and to make the coaster enjoyable. These are the equating forms. The designs begins by the defining and the initial roller coaster point and the slope of the parabola at the spot. This height point is on the left branch of the first upward opening parabola. To simplify calculations, place the initial point on the y-axis and the vertex of the upward opening parabolas on the x-axis. This example describes an initial point 25 inches above the x-axis and the slope plus or minus 2.5 at this point. With this initial data and the vertex of the first upward opening parabola can be determined. Because of the parabola vertex is involved in this calculus, the vertex of equations used. Y minus k is equal to a into x minus h square, and for the slope the derivative of this equation is also used. y equal to 2a x minus h. Substituting the proposed value, we obtain systems of equation. Solving the system, we find that a is equal to 1 by 16, h is equal to 20. The equation for the first parabola is then y equal to p1x 1 by 16 x minus 20 whole square. For the parabola with the vertex and the sum with the corresponding equation, y equal to p3x equal to 1 by 16 x minus 56 whole square, and the parabola with the vertex, the corresponding equation y is equal to p equal to 1 by 16 x minus 84 whole square. The corresponding of the vertex of the downward operating parabolas and the middle of the corresponding of the vertex and the upward opening parabola determine the height of the vertex of equation. This is the equation. For equation y is equal to p is equal to 1 by 16 x minus 20 the whole square. The marble has its maximum height and the marble's initial velocity at the point is 0. F is equal to 0, 25. V is equal to V of 0 is equal to 0. The previous comparison shows that the marble will stop at the point with the horizontal distance from a origin between 34,907 and 34.908 inches, reaching a height of no more than 13.89 inches. It is responsible to place the vertex of the second parabola at the above 13 inches height. Placing the vertex of parabola 2 at the middle parabola 1 and 3 vertex, the equation of the parabola y is equal to p of x is equal to 13 plus a x minus 30 whole square. To find the values of coefficient a, the conditions of parabola 1 2 must be tangent to each other must be solved. This condition is expressed as two equation. P1 of x is equal to P2 of x. P1 of x is equal to P2 of x. 1 by 16 x minus a whole square is equal to a into x minus 38 whole square plus 13. That gives 1 by 8 x minus 20 equal to 2a x minus 38. Solving the system of the 6, 7 the constant a, the first tangency point can be found at a into x minus 30 equal to 1 by 16 x minus 20, 1 by 16 x minus 20 the whole square is equal to a into x minus 38 into x minus 38 plus 13. That gives 1 by 16 x minus 20 equal to x minus 38 plus 13. Grouping under solving for x minus 20 the whole square is equal to x minus 20 x minus 38 plus 208. X minus 20 the whole square minus x minus 20 x minus 38 equal to 208. X minus 20 x minus 20 minus x plus 38 equal to 208. X minus 20 into 18 equal to 208. 284 by 9. Substituting 1 by 8, 284 by 9 minus 20 equal to 2 into 284 by 9 minus 38. A is equal to 1 by 16. 284 by 9 minus 20 divided by 284 by 9 minus 38 equal to minus 13, 116. Conclusion. To accurately model every component of the roller coaster designs, a branch of math called calculus is needed. Calculus used to create and analyze the curves, slopes, and twists along the roller coaster track. It helps with slope conclusions and to find the maximum and the minimum point of along the track. By this, I conclude my case study. Thank you.